Okay, so now we're going to talk about the theoretical inference from means. As for proportions, there's a central limit theorem. It says that when we choose random samples of size n from a population which has mean mu and standard deviation sigma, the collection of all the sample means you can get is reasonably normal if the sample size is large enough, say greater than or equal to 30. It's centered at mu, the population mean, and the standard error, the standard deviation of the sample means, the standard error is sigma over the square root of n. So let's see that in action first. This is a histogram of 3,000 houses, the prices of 3,000 houses for sale in Dane County. Notice that it's very, very much not normal. It's totally skewed to the right. We're thinking of this as the population of all houses that were for sale at that time. Notice that the mean is 319,000 and the standard deviation is 288,000. What the central limit theorem says is that if we look at sample means for samples of size n, say 100, then the sample means themselves will be centered around the same 319,000, and the standard deviation, the standard error, the standard deviation of the sample means, the standard error will be about that 288,000 divided by the square root of the sample size. And we can see that with the help of Stackey that, yep, that's what's happened. This is a dot plot of random samples from that last data set. So each dot represents the average of 100 randomly chosen houses from that last data set. Notice that these sample means, there's 2,000 sample means here. Notice that these sample means are centered around the same place, 320,000 in this case, or 321,000 if we round. So they're centered around the same mean as the whole population. Notice that this is much, much, much more normal looking. It looks much more like the bell-shaped curve. And the standard error is about 28,000, 28,600. So it's just what the theory told us, that even if the original population is really skewed, when you look at sample means, they tend to be normal, centered in the same place, and the standard error, the standard deviation of the sample means, is less, depending on the size of the sample, much less maybe. From 288,000 to 28,000, that's a big jump. So that's the central limit theorem for means, and from there we'll get inference very similar to the way we did with proportions. Now for inference, the story is a bit more complicated. We don't know the population standard deviation, so we have to estimate it using the sample standard deviation. And that introduces some wrinkles that are different from proportions. But for doing inference for now, starting now, we're going to use technology, an inference template on our website. And in class, we'll talk about those wrinkles and what's going on behind the scenes in the theory. But the basic idea is that if we know them, the basic idea is that the sample means will follow roughly normal distribution, and we can use that to do both confidence intervals and hypothesis testing, just as we did before. So let's look at an example question. At a large state university, 25 randomly chosen students were asked how many hours per week they spend in paid employment. And we get a sample mean, x bar, of 13.7, and a sample standard deviation, s equals 6.1. Remember, we use s instead of sigma because this is just a sample from the thousands and thousands of students at the university. And from this, we want to find a 95% confidence interval for the mean number of hours of employment, paid employment, for all students at the university. So from this 25, we want to draw conclusions about the whole university. So now let's leave our PowerPoint, and we're going to go into this inference template, inference procedure template from our website. Notice it has 4 sheets, and we're going to use the one for one mean, and we do one mean confidence intervals. So we enter our data. The sample size was 25. The sample mean was 13.7. Sample standard deviation was 6.1. And we want a 95% level of confidence. So our confidence interval is 11.2 to 16.2. And let's just copy that. And before we do anything with that, let's notice that with this template, it's really easy to see what would happen if we wanted a 99% confidence interval. Or if we had the same sample mean and the same sample standard deviation, but for a much larger sample size. Everything just changes for us. Let's go back to what we had before and write our conclusions clearly. We are 95% confident that the mean number of hours of paid employment for all students at the university is between, well, what were our numbers? Let's look at them again. 11.2 and 16.2. And 16.2. And remember, this does not mean that 95% of the students work between 11.2 and 16.2 hours. It means we're 95% confident that the mean number of hours of paid employment for all students is in that range. So there's one number we're interested in, the average for all the students at the university. We're 95% confident that it's in that range. And that's quite a big range. It's a 5-hour range. The reason it's so large is because our sample size was pretty small. Let's look what would have happened if we had just found that same sample mean, same sample standard deviation, but for a sample size of 200. Oh, now it's down to a much smaller confidence interval, 12.8 to 14.6. And notice that this template gives us the standard error, it gives us the margin of error, and some things we'll talk about in class. So that's how we do confidence intervals using the ideas of our central limit theorem. Since the sample means follow normal distribution, then our particular sample mean isn't going to be too far away from the actual population mean. How about hypothesis testing? Well, let's do a hypothesis test. Do students at the same university average less than 8 hours per night of sleep? Random sample of 25 students finds a sample mean of 7.5 and a sample standard deviation of 1.4. Notice 7.5 is pretty close to 8. So they're not very different. It's not very much different if there's different, but is it different? What does the hypothesis tell us? So let's do a hypothesis test. So a research question was, do students spend less than 8 hours per night sleeping? Well, what's our null hypothesis? Is that the mean equals 8. Null hypothesis always comes with the equal sign. Null hypothesis, the mean is less than 8. And so what we're trying to figure out is, how surprising would the data we got be, the sample mean of 7.5, how surprising would that be if the null hypothesis is correct? If the mean is actually 8, would it be surprising to get a sample mean of 7.5? That's how hypothesis testing works. So to get our p-value, well, sample size is 25, that's there already. So now we're in the one population mean hypothesis testing portion of our template. And our sample mean was 7.5. Our sample standard deviation was 1.4. And the null hypothesis was that the mean was 8. And our alternative was mean less than, so we're looking on this line, and there it is. The p-value is 0.043. Okay, so we can now, we're just back to hypothesis testing. The only thing new here is how we found the p-value. We reject the null hypothesis. Why? Because the p-value is less than 0.05. So we've made an agreement that when the p-value is less than 0.05, we reject the null. What does that mean? Well, we've rejected the null. Whenever you reject the null, you should imagine taking the alternative and striking it out. That's what it means to reject the null. Oops, excuse me. You reject the null. It's the null that you strike out. We rejected the null, and what we're left with is the alternative. So we reject the null hypothesis. We're left with the alternative hypothesis. That is to say, our conclusion in plain English is we have evidence that the mean sleeping time for students at this university is less than 8 hours per night. And then finally, a fifth step, the rationale. Why did that p-value lead to that conclusion? Well, we said it. If the mean sleeping time was 8, there would only be a 0.043 probability of getting a sample mean as low as or lower than 7.5. The data we observed would be surprising if the null hypothesis were correct. That's why we're rejecting. That's why we always reject. We reject the null if the data would be surprising were the null true. Okay, so we'll talk in class about some of the details of why this works, but basically it works by the central limit theorem. The sample means follow a normal distribution, and 7.5 is just too far away from 8 to be plausible. It's too far down on the normal distribution, and that's why we're rejecting. Notice that it's not a very big effect. So yeah, students here are getting less than 8 hours of sleep a night, but our best estimate is that it's 7.5, which biologically probably doesn't make that big a difference. Okay, we'll get some practice in class, and hopefully this will start to come into focus.